This last section of the chapter is going to deal with what are we going to do if we're given certain properties of triangles and we're asked to set up proportions to solve for various unknowns. And what I'm going to do here is display 4 different theorems to you. And just a heads up, I really don't care that you know what this theorem is called, but I'd rather care that you know how to use it. So if you see a situation like this pictorially, or if you're given a situation where you have pieces that are represented, know how to set up that proportion from it. I could care less that you know it's called the triangle proportionality theorem. And so what I'm going to do is walk you through the 4 of them and give you examples of each along the way. And then you'll be asked to practice it on your own. So for this first one, we have that if you have a line parallel to one side of the triangle that intersects the other 2 sides. So here we have the larger triangle, QSR, and we have a line TU, which is parallel, and it intersects the other side. So it intersects QR at T, and it intersects SR at U. Then what we can say is that it divides the 2 sides proportionally, which means that RT divided by TQ is proportional to RU divided by US. So let's put that theorem to work. I'm going to call AB length X. And what we have is our 2 parallel lines. So we've got the larger triangle, and we've got the parallel side to the side CD. So BE is parallel to CD. And it does intersect AC and AD. It intersects the 2 sides. So we can set up a proportion. 5 divided by X should be the same proportion as 6 divided by 12. I could have also said X divided by 5 is the same proportion as 12 divided by 6. It does not matter. Both would be correct methods. After setting up the proportion, take the cross product. We get 6x is equal to 5 times 12. So 6x is equal to 5 times 12 is 60. Dividing both sides by 6 to solve for x, we get that x is equal to 10. I want you to now try number 2. You can try it now or at the end of the video, but I do suggest pausing it, trying it out on your own, and then moving on. If the first theorem given was the triangle proportionality theorem, which stated that if you had those parallel sides, then you would have the proportion, well, the converse would just tell you the reverse of that. If you're given that you have a proportion, so you have that RT divided by TQ, RT over TQ is equal to RU divided by US, so the proportion holds true, then you can state that, well, yeah, these 2 lines are parallel. So TU is parallel to QS. In the next example, I'll put it to work. So now we want to show, is this parallel? Well, we're looking at QT and RS. And now notice in the picture, no, these do not look parallel at all. But do not depend on a picture ever. Trust the numbers. So I can set up my ratio. We've got 38 divided by 18 should be equal to 80 divided by 36. Now I'm going to put a question mark over that equal sign because I'm not sure about that yet. I need to check that. Now when I go to reduce these fractions, 2 goes into 38 19 times, and 2 goes into 18 9 times. On the right-hand side, to reduce 80 divided by 36, I notice that both can be divided by 4. And what I get is 20 divided by 9. So notice, my proportions are not the same. I now have a common denominator, but 19 and 20 are not the same number. So this is not a proportion. These ratios are off. So in this case, when asked to tell if these are parallel, we have no. These are not parallel. Now I want you to try number 4 on your own. This next theorem kind of extends what we were looking at, but it extends it to 3 parallel lines. If we have 3 parallel lines, then the ratio of the distance between them should be the same. So UW over WY should be the same ratio as VX over XZ. We'll put it to work in an example in the next page. Here's a situation where we have three parallel lines, so our ratios should be the same. So what I can do is first take the ratio of 6 divided by 4, which should be equal to GF divided by 6. 6 over 4 is equal to GF divided by 6. Taking the cross product, we get 6 times 6 is 36 is equal to 4 times the length GF. Divide both sides by 4, and we get that GF is equal to 9. So I'm going to write that down on my figure now. And basically, we're going to do this step by step. So now that I have GF, I can find FE. Same, similar method. I'm going to take the ratio of CD over CB should be equal to the ratio of EF over FG. So I'm taking this ratio over this ratio is equal to the ratio here, EF over FG. So now CD is 4 divided by CB is 6 should be equal to EF is what we're looking for divided by FG, which we already found was 9. Taking the cross product, we've got 6 EF is equal to 4 times 9 is 36. Divide both sides by 6, and EF is equal to 6. Now I found EF, I found GF, so I can write those down. Here's 6 down here. GF we said was 9. Now I have to find CF. Now I'm going to focus on similar triangles. So we got the smaller triangle and the larger triangle, and we're looking for CF. So what I can set up here is 4 divided by 5, so we've got AB over GB should be the same ratio of AC over CF. So plugging in the numbers that we know, AB is 4, GB is 5, should be equal to AC is 4 plus 6, so that's going to be 10 over CF. Finding the cross product, we've got 50 is equal to 4 times CF. And solving for CF, 50 divided by 4 is 12.5 is my length of CF. Yes, it's okay to get a decimal. Don't freak out. The last theorem in this section focuses on an angle bisector. So remember that an angle bisector splits an angle into two congruent pieces. And whenever you have that array bisects an angle, splits it in half, then what you have is it divides the opposite side, so side AB, into segments whose lengths are proportional to the lengths of the other two sides. So AD over DB, the ratio of the side that it's splitting in half, is equal to the ratio of the adjacent side to AD, so AC or CA, and divided by the adjacent side to DB, which is CB. I'll put it to use in the next example on the next page. So I'm going to do 2 examples, and then you're going to try number 9 on your own. This first one here, we do have an angle bisector. So the ratio of x divided by 4 must be equal to 9 divided by 6. But notice here, I put x in the numerator, 4 in the denominator. So in the numerator of the second ratio that I set up, I must have the side next to side length x. So 9 is next to x, and 4 and 6 must match up in the denominators. Solving this, take the cross product, we get 6x is equal to 4 times 9. So 6x is equal to 4 times 9 is 36. Divide both sides by 6 to solve for x, and x is equal to 6. For number 8, it's pretty much the same exact setup, except now we have an expression, x plus 3. So I can take x divided by x plus 3. The ratio of that side that's being split in half is equal to, or is proportional to, x, the side next to it, is 9, so I'm going to put a 9 in the numerator, 13 in the denominator. It should be proportional to 9/13. Take the cross product. 13x is equal to 9 times, I'm going to use parentheses, x plus 3, to remind myself to distribute the 9. So distributing the 9, I get 13x is equal to 9x plus 9 times 3 is 27. Subtract 9x from both sides. I get 4x is equal to 27. Finally, I divide both sides by 4, and x is equal to 6.75. Yes, decimals are okay. Go ahead and try number 9 on your own, and those are the end of the notes.